Welcome back, everyone. Welcome to the first lecture of this course. So we are going to start with very simple stuffs to warm up. So let me get quickly into the content of the lecture. So today we are going to look at the need or the purpose of introducing imaginary number. In fact, one of the first things to do in analysis, right? Because that is what motivates us to look into complex numbers and then look at complex functions and so on. So before we reason out the need for the imaginary number I, so let's look historically the the way the modern analysis came into being. So you see, till the invention of before the invention of differentiation or integration, which is the calculus by Newton and Leibniz, most of the modeling that we were doing to understand things around us reduced to algebraic equations. It was calculus that made it possible to model much more difficult problems using rate of change and so on, and and all that led to differential equations. Before that, it was all algebraic equations. That was what we were trying to understand and study and solve and so on. And the modern analysis, in fact, the purpose of this course and everything, I mean, contents of this course, everything, whatever we call modern analysis, was developed rigorously in order to understand differential equations, to solve differential equations, because it's only after differential equations came into being we started asking questions on what a function is, what a continuous function is, and give definitions which are workable and so on. Before that, most of the definitions were intuitive, right? And intuitive definition is fine, but they were not really useful while working on problems. So we need to translate the intuitive definitions into working definitions which can be used to solve problems. So if analysis is the content of this course, then you should understand that analysis grew out of trying to understand differential equations, which actually came out as a result of invention of calculus and so on. So let's start with algebraic equations to begin with, right? In, in fact, the need to introduce complex numbers comes from algebraic equations. So before the invention of calculus, the algebraic equations were the one that we were trying to solve, and one of the simplest of the algebraic equations are the polynomials, right? So in fact, even when we define the nth root of a real number, what we are trying to do is solve a polynomial of degree n. So that's a very which is an algebraic equation. So what is a polynomial? So a polynomial in one variable. When we say one variable, the unknown is only one, which is x. So a polynomial a polynomial in one variable of degree n is a map from R to R, which has this form. Whatever you see here, it has this form. So you are given coefficients, which is actually n plus 1 coefficients, which are coefficients of the power of x, right? These are all given, and what is unknown here is the x, or this is something that modeling. So once you solve for this, what you get is an x, and that is precisely probably translating something that we were trying to model. And a constant function is actually a polynomial of degree 0. So when a1, a2, a3 up to an is 0, so it's just a function of f of x is equal to a naught. So this is a constant function of degree 0. So every constant function is is a degree 0 polynomial. So what are the zeros or roots of a polynomial, right? So the zeros of the zero of a polynomial, or actually for that matter any function, not just polynomial, is precisely where the function attains the value 0. That is, if you plot the graph of the function, the points where it will cross the x-axis, it will intersect the x-axis. So these are what are called the roots or zeros of a polynomial. So for a 0-degree polynomial, what are the roots? So if the constant function is the 0 constant function, then the entire domain is where it will achieve 0. So it has infinitely many roots. Now when constant function which is non-zero has no roots because it's never going to intersect the x-axis. So it has no roots. For a 1-degree polynomial, it's of the form ax plus b from the definition that we have already seen. A and b are the given numbers, and because we are saying it's a 1-degree polynomial, the coefficient corresponding to x, that is the first degree, should be non-zero, because if a is 0, then it's going to be a 0-degree polynomial. In fact, that's part of our definition. I forgot to highlight it, that I have said here in this definition that an is non-zero, which basically means that the coefficient of the x power n is not 0, which means that this polynomial is precisely of degree n. It is not of a degree less than n, because if an is 0, it becomes a degree n minus 1 if an minus 1 is non-zero, and so on. So without loss of generality, we assume that the coefficient of the leading order is non-zero, which means that we are working with the degree n polynomial. So when we say 1-degree polynomial, naturally we are assuming that a is non-zero. So if a is non-zero, this is a 1-degree polynomial. What are the roots of this polynomial? It's very easy, which is known for a very long time, right? From as early as probably algebraic equations came into being, that the solution is x is minus b over a. It's just a simple arithmetic, right? And this precisely gives the point where this 1-degree polynomial intersects the x-axis. 1-degree polynomials are always lines, right? They are actually linear functions, or what are called affine maps or linear maps, right? When b is 0, it's a linear map, it's an affine map. So this has exactly 1 0 because it's an monotonically increasing or decreasing function. It's going to intersect x at exactly at 1 point. So 1-degree polynomial has precisely 1 0. We had seen that a 0-degree polynomial except the 0 function has no 0. So 0-degree polynomial at no 0. 1-degree polynomial has exactly 1 0 from what we have computed here. Okay. Now then comes the second degree polynomials, which are called the quadratic equations. So quadratic equations are of the form ax square plus bx plus c, where again, as I said, a is non-zero. Now quadratic equations, again, the solution to this was known as soon as even again as early as probably this equation is known, because people are very quick to look at the roots of this. They actually had a formula which is very common knowledge nowadays. So there's a very simple derivation to obtain these roots, right? So just for completeness sake, we will go through it, one of the simplest proofs. So we are looking for x such that ax squared bx plus c is 0. So we just divide by a, which we can do because a is non-zero. So x squared plus b over ax is minus c over a here. I just brought this one independent of x variable to the right hand side. Now what you do, you just convert this term here into a perfect square. So you add and subtract this term b over 2a square so that this term becomes a perfect square, right? In the sense, this term, so we are adding precisely b over 2a to this because we have a b over a here, so there's an x square here, there's a b by a x, so this is 2 times x, 2x into something, right? And that is this quantity. So x plus b over 2a whole square is this quantity, simplifies to this. So now to solve for x, you just take the square root, which gives you a plus or minus here, and then bring this b over 2a independent of x term to the right hand side. So you have a formula for the roots. So now this is going to give you, and this plus or minus sign is precisely two possible values. So it actually says that this second degree polynomial can have at most two roots. Whether they will always have exactly two roots is not clear from here, but it's exactly, it will have at most two roots. So there are three cases. So there are three situations depending on this, depending on the sign of this b square minus 4ac, which is called the discriminant, right? So depending on the sign, what happens? So when this b square minus 4ac is positive, we have exactly two distinct real roots, because this corresponds to the situation where these quadratic functions intersect the x-axis in at precisely 2 points. So you get these two roots from the formula there, right? Because whenever the second degree polynomial has positive discriminant, the graph of the polynomial will always be lying on both sides, both on the upper and lower half plane. It will pass through both the planes, so it has to intersect the x-axis exactly at 2 points, because for second degree polynomial, it's usually there is actually only one curve that happens, the way you see in your picture here. So you will have two roots for the positive discriminant case. Now for the zero discriminant case, that is when b square minus 4ac is 0, you will have exactly one root, and this corresponds geometrically to the situation where the graph of the polynomial is touching the x-axis, is just touching the x-axis, it doesn't pass through it. So you will have exactly one root in this situation, uh, and in this case, you can also see that because it's touching at the x-axis, the 0 is actually a double root, or in the case of course in this case, because second order, it's a double root. And double root basically means that that point is also the 0 of the derivative of the original function. So it is 0 of this function, and this point is also 0 of the derivative. In this case, as you can see immediately, that the slope of the tangent here is 0, right? So I mean, 0 of the derivative basically means that the slope of the tangent is 0. So this is a double root here. So one can interpret, so the idea of mentioning this here is to say that we started with a second degree polynomial. In the positive discriminant case, we got two roots. In the zero discriminant case, we get one root, but we can interpret this as multiplicity of this root. So the double root basically means multiplicity of this root. So this can be seen as a root of this function twice. Okay, this, I mean, the advantage of this you will see later. This was all only from hindsight, or from a kind of retrospective way. In the early days, we just had exactly one root. We didn't worry about double roots. And then the situation, third possibility is the negative discriminant, which basically means b square minus 4ac is negative. This precisely corresponds to the situation where the graph of the function never touches the x-axis, right? Which means there is no root. There are no roots, so there is no zero to this polynomial. For instance, if you take this function x squared plus 1, the graph of this function will always lie above the x-axis, right? And this can never attain zero, so we cannot expect a root for this polynomial at all. So we have first come across a situation so far, other than the non-zero constant function, that there are no zero situations available here. And if you recall from your complex analysis, we say that um, we introduce a root to this x square plus 1, and that is how we start our complex analysis. But there is no reason to do that here, you see, because when x square plus 1 has no solution, it is no solution. There is no reason to imagine a solution to x square plus 1. For any real number x square is always positive. So x square is never going to take minus 1. So there is no solution to this. There is no reason to imagine a solution to this polynomial x square plus 1 equal to 0. So that is not the reason to introduce imaginary number, not to solve this problem, not to give a notion of solution to this. It comes much later, which is what is the purpose of this talk. So now we have seen the second degree polynomial, which is a quadratic equation, and we had a formula for it, and we have given three possible situations depending on the sign of the discriminant. Next, let's move to the cubic equations. So for the cubic equations again, so this cubic equation actually has a very interesting story behind, story in the sense that see, those days there is no one who's going to pay you for publishing scientific articles and so on. But there was a kind of competitions that people have among, like, someone poses a problem, and if someone solves it, he gets a prize and so on, and he also shows that he is smart and intelligent and so on. So when people discover formulas, they keep it a secret. They don't announce it, so that whenever there is a competition, they can use it to solve problems whenever it's posed to them. So in that sense, the roots for cubic equations were actually independently discovered by two people, um, Scipione del Ferro and Niccolo Tartaglia. No, they never published it. They had it secretly on their own, and they did many competitions using this formula, and then solved many of these cubic equations that were posed to them. Over the years, people did realize, using their success rate, that they probably had a formula for cubic roots. And I think the story is that Cardano actually met, I think, Tartaglia, and uh, kind of convinced him to share the result and so on. And it was he who published it much later, in 1545, the cube roots of the equation. So even today, the formula for cubic roots is called Cardan's formula, because he published it, but then it was originally discovered by different people. So a cubic equation is of this form again: ax cubed plus bx squared cx plus d, where a is not equal to 0, as always we assumed. And the roots of this cubic equation, so I'm not going to derive the way, because derive the way we derived quadratic equation. I mean, one can derive it, but that's not the purpose of this course. It's a very simple thing which you can learn, and you might have come across before. So I'm just going to give the formula here. So the roots of this cubic equation can be given by this formula x equal to y minus b over 3a. B is coming from the coefficient of x square, a is coming from as the coefficient of x cube. So what is y? Y is the solution to this problem. Here again you see in this, so it's a cube root of something and cube root of something. So actually here you see whatever is inside is the same quantity, except there is a plus here and there is a minus here. So the same quantity, and the cube root of that and sum of that is y. Now here you have a, which is precisely the coefficient of x cube. What else you have is, the other thing that you have is p and q. So what are p and q? P is this quantity which is completely dependent on the coefficients of the cubic equation, and q is also something else which is completely dependent on the coefficients of q. So once you know a, b, c, d, you can solve for p and q. I mean you can solve for p and q. And once you solve for p and q, you can solve for y. Once you solve for y, you can solve for x. Right? Okay. That's the formula for. Of course, I have written it like this only because in a very limited screen size of or the slide size, so I had to show this formula. You can of course replace this y here with this formula to have a very big expression for x. And if you also include p and q, then you have a very complicated expression. So this is a very um, nice way of presenting the roots of cubic equation. Okay, so one can use this formula and solve for cubic equation. So this is something which we know from late or mid 16th century. Now this is where the issue actually starts for imaginary number. For instance, the need to introduce an imaginary solution to x square equal to minus 1 arose with the formula for roots of cubic equation. So it has nothing to do with quadratic equation. We did not want to solve x square plus 1 equal to 0 for quadratic equations. So the purpose is like this. I am going to explain to you. So for instance, take this cubic equation x cube minus 3x equal to 0. Okay. Now you can very quickly see, even without using the formula, you can quickly see that this has exactly 3 real roots, because this x cube minus 3x can be written as x cube x into x square minus 3, which is precisely x plus root 3 x minus root 3 equal to 0. So product of 3 numbers equal to 0, right? So each one, I mean one of them can be 0, so you get these 3 roots, 0, root 3 and minus root 3. These are the roots for this cubic equation. Okay, this is something which we know even without using the formula. And you see, this is a real equation. When I say real equation, I mean it's a polynomial with real numbers as its coefficient, and the roots are also all real numbers. Okay, so it's a real polynomial with real roots. Now let's try getting these roots using the formula that we derived in the previous slide. Okay, if you try using that formula which I showed in the previous slide, you know what is a, b, c, d here. A is 1, okay, b is 0, right, and c is minus 3, d is again 0. Use these coefficients to find out p and q. You will get that p is minus 3 and q is 0. Using this p and q, if you write the equation for y, what you get is this. That is, you already have a square root of minus 1 and the negative square root of negative 1. So to solve for x, you need to solve this equation, and you can solve this equation only if you introduce or solve for x square equal to minus 1. So the need to introduce the square root of -1, which is as per the theorem of real analysis or real numbers, x square is always positive. There is no number whose square can be negative. That need to introduce only as a tool to get to the real roots of a real equation. So to get the real roots of a real equation, one had to go or extend or have this freedom or venture into unknown territory, that is root -1, as a, so introduce this in the process. It will be introduced and it will also be cancelled, and finally you will end up with only real roots. That's the idea. That is how this notion of imaginary number was introduced. Okay, so it seems that even to find the real roots of a polynomial with real coefficients, one needs to venture into a territory outside real numbers and then obtain the real roots. Okay, and that's the reason why x square plus 1 equal to 0 roots of that were introduced. So this led to the notion of introducing I root -1 for the purpose of computing real roots. Now, why even introduce the symbol I, right? I mean, one can just work with root -1 because this is already a symbol. Root -1 is already a symbol. You might say it's for simplicity. Yes, it's for simplicity, but there is a specific reason for introducing this simplicity. I mean, this I for simplicity is that of this property which the real numbers had, that square root of the product is product of the square roots. Now, this one has to be careful. So when we take the square root of product of square root of -1, what we should get is -1. But if we use this formula here, you might actually get 1, right? So if I don't introduce this I and if I work with just root -1, it is possible that in the calculation I might just write this as 1 instead of -1, and just to keep track of this small symbol or error, we wrote root -1 as an I, and I square was always -1. So wherever we had a square of I here, we had to write it as -1 and not +1. That is a reason for introducing the imaginary number I. Now, with this introduction of imaginary number I, there was a lot of convenience that came in. For instance, if we go back to our quadratic equation, right, the case where we had negative discriminant and we said there is no real solution to that problem. Now one can introduce this root -1, so square root of -1 as I there, and actually come up with complex roots to that quadratic equation, right? You are all aware of that. So the advantage, so this actually extends, so the case where we did not have any real solution actually admits a complex roots or complex solution to that problem. For instance, let's take this x square plus 1. This has no real roots, but what we are doing now, we are going for a extension of x square plus 1 into the complex domain. So we are looking for a function in the complex plane whose restriction on the real line is precisely this polynomial, and look at the roots of that, and this complex polynomial has exactly two roots, which is plus or minus I. But the issue is here we just naturally took the extension to be, when maybe had x square plus 1 equal to 0, so I'm going to take this polynomial natural extension, I'm going to take the complex polynomial x square plus 1 and we solve it. Yeah, it worked, yes, but there is not always a unique way to extend a real function as a complex function. There are more than one way to do it at the first instance without imposing any additional condition. Like for x square minus 1, in in addition to z square plus 1, I could have also extended it as real part of z square plus 1, which again, when restricted to the real line or to the real numbers, will give you this original polynomial. Another possibility is also this extension where z, it is z square plus 1 when the imaginary part of z is 0, and when the imaginary part of z is non-zero, you just put 0. So this again is an extension where when restricted to the real numbers is x square plus 1, outside the real line it's actually the 0 function. So these are all possible extensions to this. So when we say I'm going to look for roots of a complex extension, why is this extension, that is a z square plus 1, the right extension or the natural or nice extension, and not these extensions which I have given here, right? These are all the questions, these are all things which we see when we study complex function theory. So these are the questions that leads one to study holomorphic functions and analytic continuations of real functions into complex domains and so on. Okay, so these are the motivations of getting into these subjects. Now, for our case, what we have done is that the question is, we had a real polynomial, we were looking for real roots. It turned out that in the real situation you have no roots possible, but it turns out that the problem ends there just by introducing complex numbers. So we don't have to introduce more imaginary numbers or other things to solve the polynomials or these algebraic equations. So once we have introduced the imaginary number, the complex number is algebraically closed. That means if you take the polynomials of degree n in the complex domain, then they will all admit complex roots. And this is the statement of the fundamental theorem of algebra, which tells you that complex polynomials or polynomials with complex coefficients admits exactly as many roots as the degree of the polynomial, which is precisely saying that C is algebraically closed. So the roots are always in the complex plane and you don't have to venture beyond complex numbers. Okay, so in the next lecture we will look at a proof and the statement of the fundamental theorem of algebra. Thanks a lot.